Hello and welcome to this manufacturing systems technology part 2 module 29. We will be mostly dealing in this module with issues related to robotics and some issues related to factory automation. Let us look at robotics and how historically robotic systems really emerged. The first articulated arm which can be associated with the sort of the beginning of the whole robotics area was developed in 1950, and this sort of articulated arm was controlled through microprocessors which were actually developed a little earlier, but then there was a lot of technology growth in the area of microprocessors in the end of 50s and 60s, which fueled this development of so called robotic systems. So now robots have become available in a variety of types, styles and sizes starting from 1950s, and they are capable of performing a wide variety of again operations in the industry. Examples could be, commonplace examples could be robots which are used for car assembly, for weld assembly, for even painting in automotive industries extensively. Robotics also are used in electronics industry for assembling of different printed circuit boards to different levels of microelectronic processing as well as assembly, etc. So there is n number of applications in the industry for these robotic systems. In fact, the driving force for the purchase of robots is their applicability in a hostile or strenuous and repetitive environments, when we are talking about producing many items with a time demarcation of producing one item for a longer range of times. So obviously if a rapid production is needed, and with more repeatability and accuracy such production is needed, and so therefore robotic systems are considered because of that aspect. Applications again, as I told you, welding, painting, pick and place, material handling, among others, is becoming now an integral part of automated discrete manufacturing, part manufacturing systems, particularly systems like flexible manufacturing systems are all applied, cannot think of the system being in place without robots maneuvering different operations or different subsystem level activities within that overall system. Let us look at some definitions of what is an industrial robot. According to the Robotics Institute of America, an industrial robot is a programmable multifunctional manipulator designed to move materials, parts, tools or specified devices through variable programmed motions for performance of a variety of tasks. The developments in the area of robotics since the first articulated arm of 1950 have been motivated primarily by development in the area of industrial automation, particularly computer integrated manufacturing systems based automation in general. We had an extensive course earlier in manufacturing systems technology part 1, where these SIM systems or computer integrated manufacturing systems were described in great details. And an industrial robot consists of a number of rigid links connected by joints of different types, controlled and monitored by a computer. To a large extent, the physical construction of a robot resembles a human arm, like you have a lower part of the arm, an upper part of an arm, a wrist, and then something like the portions of the hands which you are in question. So in a similar manner, if I can have all these degrees of freedoms with respect to a lower arm, the upper arm, the wrist and the forward hand portion of this arm, this could actually be mechanized to be implemented as a full-fledged robot arm. Let us look at such an example here and understand what are the kind of degrees of freedoms which are available. A typical industrial robot with 6 degrees of freedom has been illustrated here, courtesy of the ABB Robotics Incorporated. So here you can see the first degree of freedom is basically turning of the complete mechanical robot around the point C. The turn angles have been shown here. So the whole arm here, this whole arm is going to get rotated in this particular direction about C. The other turning can be about the point B, where the forward and reverse movement of lower arm can take place. So there is the movement of the lower arm, as you can see in the hand. So this is the movement of the lower arm. So this can occur. Okay. Again, axis 3 about A, where this is the axis that we are talking about, where the up and down movements of the upper arm can be formulated. This is the lower arm, this is the robot base for executing overall missions, and this right here is the upper arm. So, you have at least 3 degrees of freedom recorded so far. So, the movement about the point D. So, this corresponds to axis 4, it is the turning of the complete wrist center. So, let us say for example, in the human arm also, once you have positioned the upper arm at a certain angle, then you are able to sort of turn the wrist portion of the arm. So, that is given by the term D, and then finally you have another axis which corresponds to bending of the wrist around the wrist center. So, basically once the wrist center axis is enabled to rotate, you can also turn the wrist upside down and bend the wrist about the wrist center. So, that is what is meant by the axis E. And then finally, the 6th axis of the robot is by virtue of the turning of the mounting flange or the turn disc, which would do some operation. Maybe let us say we are talking about dispensing of spray paint, where there is a flange rotation which is very important to atomize the paint as an automotive industry, or then we are talking about some kind of a painting polish or buffing kind of a robotic system, where again such rotations are used for moving the buffing wheel very close to the body. So, that can be accumulated with all these 6 different motions as in a human arm, and this typically how a robotic system is classified geometrically. Having said that, let us look at the basic components of the robots. They include typically a manipulator, the controller, and the power supply source. These are what is needed. Power sources for robots. So, an important element of the robo is the drive system that the robo has. The drive system supplies the power which enables the robo to move. The dynamic performance of the robo is determined by the drive system adopted, which depends mainly on the type of application and the power requirements. Mainly 3 systems are there which applies the mechanical power to the robos. One is a hydraulic drive system, another is electric, and third is a pneumatic. Of course, there are many advantages and disadvantages of all the 3. Let us look at hydraulic drive first. So, hydraulic drive it gives the robo great speed and also a lot of strength in doing its operation. The systems can be designed to actuate linear or rotational joint, for example, and as the name suggests, it is through oil movement in certain pressurized pistons across the robo. Obviously, as a medium is involved, there are additional problems of leakages which would come in such a robotic system, making the floor particularly messy, and also the occupancy level of the floor is also high because of additional pressure cylinders and storage tanks for the oil which would generate this mechanical motion in turn. So, hydraulic drive robos are preferred in an environment where the use of electric drive robo may cause fire hazards. For example, when we are talking about spray painting in a paint shop in an automotive, obviously there is going to be paint thinner which is very highly inflammable and also volatile. So, there you cannot afford to have a electrical hazard, fire hazard. So, there is a typical application where you can deploy a hydraulic drive robo. There are electrical drive robos which are comparatively much more accurate, because obviously the electrical drive systems are better controlled. They exhibit better repeatability, they are also cleaner to use, but the disadvantages could be not as high strength or speed as can be given by hydraulic actuation, because there is a cylinder based pressure which can be maneuvered to a higher value. Unfortunately, the kind of torque RPM product that can be given by electrical drives are typically limited by the power requirements or power limitations of the motors which drive such systems. So, just as in CNC control we had earlier seen in manufacturing systems technology part 1, here also the categories of motors can be either stepper motor driven processes or direct current servo motor driven processes. This would be the high end torque application, and this would be more related to preciseness or accuracy, and I need not illustrate this anymore because we have done in great details in CNC while doing that lecture. The third type is pneumatic drive systems, which are generally used for smaller robos. These robos with fewer degrees of freedom carry out simple pick and place material handling operations, such as picking up of an object from at one location and placing it to another location. So, these are already well defined in terms of the weights that they would have to carry, and it is merely a location change. So, these operations are generally simple and have short cycle times. So, the pneumatic power can be used for sliding and or rotational joints. and pneumatic robots are much less expensive than electrical and hydraulic, because you do not need to develop much of a control system. All you need to do is to sort of actuate, deactuate the various valves in a certain sequence, so that the airflow can actually make the robo do mechanical work. So, that is how the power systems are classified, categorized. The other important component that the robot has is sensors. So, obviously, the sensors are systems which provide feedback to the control system and gives the robo more flexibility. There may be several sensors. There can be visual sensors which are useful in building of more accurate and intelligent robos. They can be classified in many different ways based on their utility. So, for example, you can have a position sensor which is used to monitor the position of joints. Information about position is fed back into the control system, and that is used to determine the accuracy of the joint movements. Accurate joint movements are reflected in correct positioning of the end effectors, which eventually carry out the prescribed task. Robot sense then there are range sensors which talk about the range of operation. So, it measures distances from the reference point to the other points of importance, and range sensing is accomplished by means of television cameras or sonar transmitters and receivers. The problems may be reduced by using a greater number of sensors. The idea is that within the robot range there should be a identification if there is any other movement in the range of movement of the robo and there is a case of collision, there has to be a self correcting mechanism which stops the mechanical activity of the robot the moment it faces an obstacle of that sort, okay, in a varying environment. Okay, so, that is one issue that is very important in the sensing. Then there are velocity sensors which are used to estimate the speed with which a manipulator will be moved. The velocity is an important part of the dynamic performance of the manipulator. So, variations in acceleration during the movements between points give rise to dynamic nature of the manipulation. Inertial forces due to changes in acceleration, damping forces due to change in velocity, and spring forces due to elongation in links caused by gravity, and the weights carried should be monitored and controlled to fine tune the dynamic performance of the manipulator, for which this continuous monitoring of velocity, particularly of the end effector or the other linkages which are associated with the robots kinematically would need to be sensed. So, the best example is a DC tachometer, which is one of the most commonly used devices for feedback of velocity information. So, it is a DC generator which provides an output voltage proportional to the angular velocity of the armature, which will be able to again back calculate the type of the speed sensing that is going on. There are going to be also proximity sensors which are used to sense and indicate the presence of an object within a specified distance or space without any physical contact. So, this is more or less similar to the range sensor. The range sensor is basically up to what range the robo will move, and some range sensors are also serving as proximity sensors from time to time. But there are independent proximity sensors which will only do the job of sensing the presence of a foreign object within a specified distance or space, and these sensors are typically working on reflected signals. So, any such object comes on the path as an obstacle, it reflects the light back to the source, and they receive this from the object, and these signals are generated using maybe LED transmitters and are received by a photodiode receiver sort of a arrangement. But as soon as you get a signal, the idea is to sort of mechanically change the path or track of the robo to avoid collisions. So, there are many other type of sensors with different sensing abilities. For example, acoustic sensors sense and interpret acoustic waves in gas, liquid or solid. Touch sensors sense and indicate physical contact between the sensor carrying object and another object. Force sensors measure all the components of the force and torque between two objects. Tactile sensors are developed to provide more accurate data on the position of parts that are in contact, and that is provided by the vision, so on and so forth. So, we now talk about robot movement and precision. So, speed of response and stability are two major important characteristics of robot movement. The speed defines how quickly the robot arm moves from one point to another, and stability refers to the robot motion with less amount of oscillation. A good robot is one that is fast enough, but has the same time at the same time has good stability. So, three important basic features which are very important to be controlled is spatial resolution, the accuracy and the repeatability. So, the speed and stability are often considered as conflicting goals. However, a good controlling system can be designed for the robot to facilitate a good trade off between the two parameters. And the three important aspects, the three basic features which are there in any robotic movement and precision description is spatial resolution, accuracy and repeatability. So, definitionally the spatial resolution is the sort of the smallest increment of movement into which the robot can divide its work volume. It depends on the system's control resolution and robot's mechanical inaccuracies. So, if supposing the control resolution is sort of not very high standard, then it may mean that the amounts of increment that the robot moves in its motion pathway may be higher, and that also this increment can probably be unstable because the increment may keep on changing or varying. So, that is how the spatial resolution is defined. Let us now talk about a numerical example how you will find out. Let us say a robot's control memory has 8-bit storage capacity, it has 2 rotational joints and 1 linear joint, and you have to determine the control resolution for each joint if the linear link can vary its length from as short as 0.2 meters to as long as 1.2 meters. So, obviously, if the control bit memory is 8-bit, that means the number of increments that can be programmed into the system are exactly 2 to the power of 8, it is a binary number, so around 256. So, with this kind of a storage capacity, the total range of the rotational joint, for example, if the joint were to rotate 360 degrees, would actually be equal to 360 by 256, that is about close to 1.4 degree resolution, right. So, this is the resolution. So, basically you can see now that how the capacity storage of the controller or the control memory of the robot is directly related to the ability to store small increments. So, therefore, in this case, if the robot has to be positioned at less than 1.4 degree rotation, it is not possible, okay, because the robot's controller is giving a resolution of 1.4 degree and above. So, that is the minimum sort of a least count movement in terms of rotation which could be executed in this particular robot. Similarly, if the range of the robot is from 1.2 meters to 0.2, that is about 1 meter, the resolution that this would have is again 1 meter by 256, that is about close to 3.906 millimeters. It obviously means it does not, so between let us say 3.9 or 4 millimeters is the resolution. So, if I wanted to position at an accuracy of less than 4 millimeters with this kind of a 8-bit storage capacity, it is not possible in doing the less than 2 millimeters or less than 4 millimeters positioning. So, that is how you define the spatial resolution part of the robot. There obviously accuracy, which can be defined as the ability of a robot to position its wrist end at a desired target point within its reach. In terms of control resolution, the accuracy is defined as 1/2 of this control resolution. So, supposing there are 2 control points which are 4 mm distance, the accuracy should be at least 2 mm for it to be enabled to position. That is the whole idea behind accuracy. Okay. So, the reason is the displacements smaller than one basic control unit can neither be programmed nor measured on an average, and they account for 1/2 VRCU. The accuracy of a robot is affected by many factors. For example, when the arm is fully stretched and it is in full load conditions, the accuracy may be smaller because of greater deformations, etc., because of the load. And if the arm is closer to its base, then the inaccuracies tend to be minimal because now you have less loading conditions on the robo arm, etc., obviously. So, the accuracy also is a dynamic phenomena. It keeps on changing whether the robo is fully stretched or the robo is in its base position. So, in robos only linear varying links, ideally the accuracy may be considered to be uniform, but if there are angularly varying links, etc., there are going to be many other factors like different kind of stresses because of rotational as well as linear motion, and the accuracy may change because of that. The other aspect is repeatability. So, this refers to the robo's ability to position its end effectors at a point that had previously been taught to the robo. So, if I want the robo to go to a certain point A, how much accuracy it has or how much compliance it does to going to the point A is what the repeatability would be. There is a way to measure the repeatability error, and it differs from the accuracy as given below. Let us understand this example more thoroughly. Let us say there is a point A which is the target position as shown in the figure on the right, and position A represented here in this particular figure. So, therefore, this is the position where the end effector of the robot should go once it has been programmed. Because of the limitations of the spatial resolution and therefore accuracy, the programmed point becomes point B. So, instead of going to A, the robot goes to certain point B right about here. The distance between point A and point B is a result of the limitations on the robot's repeatability, because obviously every time it is going to the program point A, there is an error which it has in going to A and it actually accidentally goes to B. However, it may not be possible or it may not be reasonable to assume that every time it will go to point B, because there can be another instance where it can go to somewhere around C, which is at more or less similar distance, or similar sort of repeatability from A as shown here. And there are a variety of such points as represented by these pluses, where there can be the robot position, programmed position, once it is supposed to go to the point A. So, the accuracy error now would therefore be represented by AB, but the repeatability errors would actually be represented by the point BC. Okay. So, one aspect is to accurately position, another aspect is when you are positioning it, how repeatably you are positioning it is the question. So, you now understand what is repeatability and there is what is accuracy. So, AB for example, in this case is the accuracy error, and BC, and there can be many such BCs, C point can be here or here or here or any other such in a certain closed domain maybe where the C's could be there. And in case of many trials you will find out that there is a bizarre set of C's which are there. The question is how well defined you make this C and what is the range within which this robot will operate so that C can minimize. So, you have a very less repeatability error which is in question. So, this typically can be represented by, let us say, this inner circle here. So, if supposing I had a lower repeatability error, obviously these are cases where the repeatability error is lower. In fact, slightly higher, but then again within the same range can also be treated. So, this is essentially the radius between which such C points would be positioned with respect to the actual point B, which is inaccurately being transversed while the programming point was A, so on and so forth. So, but then it can be a case where this is actually the repeatability error is very high and the points are actually at the outer side. So, this is how you sort of plot the repeatability and accuracy errors. A good idea is to be able to look at it from a standpoint of a standard deviation and mean, just as we did in SQC earlier, and then we can see what is the spread around the accuracy error, which would be able to give you whether the spread is more or less depending on whether the repeatability error is more or less, so on and so forth. So, this is how accuracy and repeatability can be defined in terms of robotic motions. Let us talk about robotic joints now. A joint is a mechanism that permits relative movement between parts of the robot arm. The joint of a robot are designed to enable the robot to move its end effector along a path from one position to another as described. The basic movements required for the desired motion of most of the industrial robots are the rotational movement, which enables the robot to place its arm in a direction on a horizontal plane. The radial movement, which enables the robot to move its end effector radially to reach the distant points, and obviously the vertical movements which enable the robot to take its end effector to different heights. So, these degrees of freedom independently or in combination with others define the complete motion of the end effector. These motions are accomplished by movements of individual joints of the robo arm, and depending on the nature of the relative motion, the joints are actually classified as prismatic joints and revolute joints. Here for example are showing different cases of linear joints, rotational joints, twisting joints, revolving joints, so on and so forth. This right here is a linear joint. The links are generally parallel to one another, and in some cases adjoining links are perpendicular, but one link slides at the end of the other again linearly. A rotational joint R, which is showing some kind of an angular motion of one joint with respect to the shaded joint with respect to the non-shaded one. So, it is identified by its rotational motion about the axis perpendicular to the adjoint link. Here the lengths of the adjoining points do not change, but the relative position of the links with respect to one another change as rotations take place. Obviously, there is also a twisting joint T, which is also the rotational sort of a joint, but now it is not about really changing the distance, but about changing the angular orientation of the axis 1 with respect to that of axis 2. Okay. So, that is how twisting can be described. So, this rotation involves twisting of one link with respect to another, hence the name twisting. The revolving joint V is another rotational joint where the rotation takes place about an axis that is parallel to one of the adjoining links. For example, in this particular case this is the axial center and this joint goes all round, or vice versa as has been illustrated in the figure. So, this can be typically a revolving joint. Usually the links are aligned perpendicular to one another and one of them is revolving around the other. So, this is how you classify all the different joints of a robo. Now, there is a certain way, a standard way to describe the joint notation, and I am going to just show you how to describe that. The robo's physical configuration can be described by the notation described in this section. The notation basically identifies the types of the joints that are used in the configuration of the robo. As just discussed before, the joints can be denoted by the letters L, R, T and V for linear, rotational, twisting and revolving respectively. So, if we consider the different robot arms which are here in these examples, we could be able to give a joint notation to show these arms. So, for this we consider the arm and the body first and use these letters to designate the particular robot configuration. In this particular case, this is the body, let us say this is the body portion and this is the lower arm, this is the upper arm and this is the wrist region. So, we can consider this robot to be a configuration of L, that means a linear lower arm, linear upper arm and then followed by a twisting wrist and also a rotating wrist. So, there is capability of movement, rotational movement, okay. And then again a twist on the end effector itself. So, you have the lower arm, you have upper arm, you have the wrist here and then you have the end effector here. So, this can be represented therefore by LLTRT, which means that you have a linear lower arm, a linear upper arm, twisting wrist and then also a rotational wrist and a twisting end effector. Okay. So, this is how we were describing the full configuration of this particular case A of the robot. Similarly, you can make other configurations B and C, which we will probably discuss a little bit later. So, in the interest of time, I will close this module here. And then we also have a portion of the course which is still left over, which includes how the coordinate system can be mapped from a local to a global coordinate system for the robo and vice versa, and they are basically kinematic transformations done in a similar manner as I had earlier illustrated while doing the computer aided design in the first part of this course. And I will probably like to derive some of these in the next lecture, but this lecture would be the last lecture of this whole session. It will be sort of a wrap up lecture with a little bit longer duration, about probably close to about 40 or 45 minutes, and this will be posted and it will come online on the 26th, that is Monday of October. Okay. So, on up to this particular week we are going to post only this 5 modules starting from lecture 25 all the way to lecture 29, and the 30th module will be web posted on 26th. So, as of now, goodbye, thank you.